guess that we can start. It's Sushant Sachdeva from the University of Toronto. He did his PhD here some time ago, and recently had a major breakthrough in algorithms, showing how with almost linear time all flow problems, almost all problems.
Thank you, Ran, for this introduction, and thank you everyone for coming. It's great to be here. And sort of, as I was telling Barak, it makes you feel old that it's been 10 years that I gave a talk in this building. So welcome. I will, as I said, I will talk about achieving all flows in almost linear time. This work is based on a paper at Fox last fall with several amazing co-authors, Lee from Georgia Tech, Rasmus, Yang, Richard, and Max. And this, as you can see with the list of institutions, this is really a COVID era work where everything happened over Zoom. Great. So we're going to talk about primarily about max flow and min cost flow, problems that all of you have seen at some point, at least in some algorithms course. So let's begin. Right. So maximum flow is a problem that TCS folks have been studying even before TCS was defined. Right. Am I doing something wrong with the? Okay, awesome. Thank you. So, for example, here's a graph from a textbook 1955, where Harris and Ross try to capture the capacity of the Soviet railway network by trying to formulate it as a maximum flow problem. Right. So we've been studying it for 70 years, and for very good reason. It not only is it an interesting problem in itself, it's a very powerful algorithmic primitive. And you've probably seen several easy reductions. Okay, bipartite matching can be solved via maximum flow. You can do vertex capacities. You can do several other problems, and I'll mention examples of these. And over the years, because the problem has been challenging, it has become a test bed for new algorithmic paradigms and new algorithmic techniques. Like as an example, dynamic data structures, right? If you've heard of dynamic trees, were actually defined in order to speed up the runtime of max flow algorithms. So Slater and Tarjan was in the context of maximum flow, and since then, the use of continuous optimization, interior point methods, like several other fusion of combinatorial techniques has been in the context of maximum flow. And today we'll see sort of, in some sense, a culmination of a lot of these ideas. So let's recall the problem so that we are all on the same page with respect to notation. So I'll work with a directed graph. The graph has n vertices and m edges, and we have two special vertices, a source S and a sink T. Your goal is to send flow, right? So, and in order to define my constraints, I need to define. Sorry, I'm getting a hang of this. I'm going to have edge capacities on every edge. So every edge is directed. It has an integer edge capacity. We'll assume that these are integers that are polynomially bounded for the purpose of this talk. We sort of simplify our results. So here's an example of a graph. Here's a special source vertex. Here's a special sink vertex, and the numbers in black denote our capacities, integral capacities. Right? And what is our goal? Our goal is to route the maximum amount of flow from your source to the sink, while respecting the directions of the edges and the capacities on the edges. Right? All of us familiar with this notation, right? Super. So great. So classically, right? Like as the problem was defined, very quickly folks realized that it's a problem talking of paths. So you can represent a flow combinatorially as a collection of flow paths, right? So as an example, I can send 1 unit of flow along this path, 1 unit along this path, 1 along this, and 2 along this. And here that's a flow of 5 units from the source to the sink. right? This is the classic view as a collection of flow paths. A somewhat more modern view that we will take in this talk is a linear algebraic view that a flow is actually just a vector that is assigning values to each of these edges, right? So I'll think of flow as a vector in R to the E, right? So assigning one value to every edge, and these purple numbers are all my flow values, right? Of course, every vector is not a flow vector. So what do we want these vectors to satisfy? We want it to satisfy a few constraints. The first thing we want is that it should satisfy direction and capacity. So on every edge, flow is non-negative and is bounded by your capacity, right? That's the easy constraint. The more interesting one is flow conservation, right? You want inflow equals outflow, if you remember that. To say that more, to express that more succinctly, let me add a special edge going back from the sink to the source. And on this special edge, I'm sending 5 units, which is the total amount of flow going from source to the sink, right? Once I do this, then I can express my constraint very compactly. All I need is that at every vertex, inflow equals outflow, right? So for example, at this vertex, I have three units incoming and 2 units outgoing here and 1 unit out. Right. So, and now I want this at every single vertex, including the source and the sink. Right. So, okay, I should say, feel free to interrupt me anytime. Right. We should have time for questions. So, super. So, and now your goal becomes very easy to state. Just send the maximum amount of flow along this special edge E sharp, subject to your capacity constraints and the net flow constraints. And that's in fact, this is a linear program for the maximum flow, right? Good. So we will take this linear program perspective and we show that we are able to solve this linear program and hence solve maximum flow in almost linear time. Almost linear time in the size of the graph. So that's m to the 1 plus little o. All right. So our result is actually significantly more general and can solve what we call sort of all convex single commodity flows. So how do we formulate that? So observe that I didn't write maximize the flow. I wrote it as minimize the negative of the flow on the edge. That was very deliberate because from here I can now generalize. I'm sorry, I keep clicking on the back button. So I can generalize to convex edge separable costs. Okay, so let's parse that. So I still have a flow that satisfies direction and capacities. I require net flow constraints. Now you can generalize to arbitrary net flow constraints. That's sort of a simple generalization rather than all being 0. I can have a vector here D, but the cost of the flow is now going to be a sum over your edges. Every edge can have a different cost function, cost of E, that depends only on the flow on that edge, right? But each of these functions has to be convex. Okay, so every edge has a different convex function that penalizes the flow on that edge, and you sum over all your edges, and your goal is to minimize this cost, right? Under mild conditions, we can basically solve. Sorry, we can basically solve these convex flow programs in almost linear. Is the statement clear to all of us? The kind of problems this can handle? Okay, excellent. So this gives us a lot of well-studied problems in almost linear time, and for the first time. So bipartite matching, min cost bipartite matching, min cost flow, negative weight shortest path. Like if I'm correct, last semester you saw an alternate algorithm for negative weight shortest paths, but this one also gives you an almost linear time algorithm, and many other nice problems that you might have heard of. So optimal transport, flow diffusions, all of these actually you can just get by reduction from min cost flow. But our more general formulation gives you many more. We get matrix scaling entropy regularized optimal transport, which is really which has been really hot in machine learning for the past couple of years, like measuring distances between distributions. You can do p-norm flows, you can do isotonic regression. All of these problems can be solved in almost linear. Yes. Good, thank you. So that's what I hid under the star. So the assumption we require is that each cost function has a nice and computable barrier function, self-concordant barrier function. Since it's a constant dimensional, like it's just a one variable function, it's usually like for basically any function we can write down. We already know that there are, but arbitrary convex functions, yeah, we don't have such self-concordant functions, right? So it's, and we in fact know that there exist such self-concordant functions. They may not be efficiently computable. That's the assumption we make, that for each of these single edges, each of these functions has a nice self-concordant function which we can compute derivatives and Hessians quickly. Right? Any more questions so far? Okay, excellent. So in the rest of this talk, I want to give you several ideas, but I would be amiss if I didn't compare it, sort of give you context with regards to the insane amount of work that has happened on Maxwell flow. So the first thing is I usually do is I apologize. Your favorite work will probably not be on this slide. I mean, in fact, Bob has done some amazing work on Max flow. Most of that will not be listed here. But the reason I'm listing his slide is sort of to divide the history of Max flow into some phases and inspirations, and to set our work in contrast to them, as to tell you how it's different. Okay, so starting back since the problem was studied, there have been all the original algorithms were basically combinatorial, right? So all of you might remember Ford-Fulkerson, right? Augmenting paths algorithm, find and augmenting paths and send flow along it, right? So starting from Ford-Fulkerson to Goldberg and Rao, which achieved an m to the 1.5 running time in 98. These were all taking a combinatorial view of flows, working with augmenting paths, blocking flows, vertex potentials. And I want to sort of make a point here that all of these algorithms sort of had combinatorial outer algorithms and combinatorial inner algorithms. What do I mean? So let's think of Ford-Fulkerson. Ford-Fulkerson says, construct the residual graph, find an augmenting path and send flow along it, construct a residual graph again, right? So I want to break this up into an outer inner loop. So the outer loop is constructing a residual graph at every step, and the inner loop is just find me an augmenting path, right? So both of these steps are combinatorial, right? So after Goldberg and Rao, there was sort of almost no progress for almost a decade, and this bound really stood for a long time. A decade later, Deitch and Spielman actually gave another m to the 1.5 algorithm, not better yet, but with a very different approach. The approach they took was that they combined interior point methods with Laplacian solvers, and sort of began what is called since then the Laplacian paradigm of combining continuous optimization algorithms to solve these linear programs with graph theoretic insights in the inner problem. Right? So to just spell that out better, what they proposed was that you use an interior point method to solve the linear program for max flow. That's your outer algorithm. So you have an outer algorithm that's numerical. You get an inner problem. So specifically in the Deitch-Spielman work, you get an inner problem that says compute an electrical flow in the graph, which is now a somewhat more numerical problem than finding, say, augmenting paths. Right? So since Deitch and Spielman, all progress on this problem has been based on combining these continuous optimization methods along with graph theoretic interpretation. So you get a numerical outer algorithm and a numerical inner algorithm. And the paradigm sort of worked with that, hey, we try faster and faster outer algorithms. So by default, interior point methods require root m to the 0.5 iterations of the outer algorithm. And each inner problem, electrical flow, we knew how to solve in almost linear time, but we tried to work with stronger and stronger primitives. So over the years, several works improved the iteration count of the outer algorithm. Right? If you've heard of Madhuri's work, that sort of for the first time in a long time beat the m to the 1.5 barrier, and all the follow-up work since then, they improved the outer interior point method, right? But there was sort of still no hope of getting down to linear, because hey, you can go from m to the best hope here was to go from m root m down to like m to the 1/3 iterations. But each inner iteration is requiring linear time, so you'll still be at m to the 4/3. That was where we were shooting towards. Last few years, folks trying to speed up the inner algorithms via dynamic algorithms. Like these are problems that are changing slowly from iteration to iteration. Can we solve them faster in an amortized sense? And they achieved like a hairline improvement over m to the 1.5 in the general case, m to the 1.48 or something. And we, in contrast, so we basically achieved almost linear time. So let me tell you, how do we compare in this setting? So we use a slower IPM, much longer number of iterations, almost linear number of iterations. But interestingly, the trade-off is that we get a combinatorial inner problem, right? There's one that has a more combinatorial inner structure, and that allows us to use dynamic algorithms to solve each of these problems in basically constant amortized. And you combine this and you get an almost linear time, right? So it's a slower IPM, but we use dynamic algorithms to solve this sequence of problems faster. Okay, questions? Okay, excellent. So in the rest of this talk, I first hope to tell you quickly about IPM. This should not take us long, and then we'll spend some time picking up a few key ideas about what goes into the data structure. All right, so as I said, these outer algorithms are interior point methods. So let's talk of our first key ingredient, which is an L1 interior point method. So let's first generally just discuss how interior point methods solve linear programs, right? So let's say here's a linear program. These are the facets of the polytope, and I want to minimize a linear cost over this polytope. So the classic, the first provably guaranteed IPM was by Karmarkar. He defined a potential reduction interior point method that works as follows. So he gives a potential that looks somewhat magical, but let's parse this. It consists of two key terms. The first term is an objective that very rapidly decreases in the direction of the cost. So it's a log of the cost at the current point minus your guessed objective value, right? So it's decreasing logarithmically, but there's a factor m outside. So it decreases very rapidly in the direction of your cost. Okay. The second term is interesting. You get one term for every facet, right? So remember, what was our constraint? We want the flow to be bounded between 0 and the capacity UE, right? So for every edge, I add two terms, minus log FE and minus log capacity minus FE. So you add two log terms per edge. That basically force you to say that my flow should not be very close to 0 or very close to capacity, right? So if I put these two terms together, so the first one says we are going to improve the objective. The second one keeps it far from your hard constraints, right? Like these hard inequality constraints that we have in a linear program. You put them together and you get a potential function, a non-convex potential function over your polytope, right? And the recipe now is that we will start with an initial point inside the polytope, strictly inside the polytope, and from there we start to make local improvements. So from F0 we move to F1, improving the potential a little, then to F2, and then so on. And once you've made enough progress just by the shape of the potential function, you're guaranteed that you will be close to the boundary. Once you're close to the boundary, we know max flow has integral solutions, so you can basically round to an optimal solution. Right? This is how interior point methods generally work. This was Karmarkar's interior point method. Okay, so the missing thing that I have not specified is how do you take these local improvement steps? How do I move from F to F plus delta while improving the potential? Right, so let's talk of this one step of interior point methods. So the recipe Karmarkar proposed was, okay, let's look at the potential function. So let's say I'm currently at point F. I want to move to F plus delta. Look at your potential function and write a second order Taylor expansion. Right. So that means F plus delta, the potential at F plus delta, I bound it by the current potential at F, a linear term given by the gradient, and a quadratic term given by your Hessian. Okay, so let's observe that so if you remember the potential, it had two terms, right? Cost term and these log barriers. We are going to ignore the cost term for looking at the Hessian. Okay, the cost term is involved in the gradient, but ignore the Hessian. For the second term, the log barriers, the Hessian with respect to each flow variable is just a scalar, right? It basically gives you with respect to the entire flow vector, you get a diagonal Hessian. Right? Let me maybe go back just a second. Sorry, wrong direction. Okay, so look at this log barrier. If I'm focusing on, there are no cross terms basically. There's no term that involves FE1, FE2. Right? So the Hessian is diagonal. So I will write the diagonal Hessian in a slightly special way. So you get sum over LE squared delta squared, right? A diagonal Hessian term. These LEs are what I will call lengths. I'll assign lengths to the edges, right? So these did not exist in the original problem, but out of the Hessian of the potential function, you get these lengths for the edges. And what is the length? The length is, okay, I'm sorry for this zoom pop up here. Let me move this. The length of an edge is the inverse of the symmetrized residual capacity. Okay, what is that? So it's 1 over minimum of Fe and minimum of capacity minus Fe. Okay, let's spend a minute discussing why does this appear. So let's say I currently have flow Fe, right? How much can I reduce the flow by without violating the non-zero constraint? I can reduce it by Fe at most, right? And how much can I increase the flow by without violating the capacity constraint? It's UE minus F. So you take the smaller of the two and you take the inverse. That gives you the penalty on that edge as the length. Yes? Does this make sense? Can I answer questions? Okay. So you write the second order Taylor expansion and we will optimize. We will optimize this function over steps delta that do not change your demands, right? So they are circulations. This becomes equivalent to the electrical flow problem, right? So in some sense, what I've described to you is roughly the recipe of Dietz-Spielmann. Like you take an IPM, you get an electrical flow problem, you can solve it in almost linear time. Okay, so what did we do? So this is all Karmarkar's IPM, and this was already observed before. We proposed upper bounding this potential function with something strictly worse, going from L2 to okay, sorry. So I have a visualization to help us parse this. So yes, you want to make the potential smaller and smaller because it reduces in the direction. Yeah. Thanks. It reduces in the direction of the cost. Okay, so let's visualize what's happening. I think this this graphic is very helpful. So you're at a point F. You draw an ellipsoid around. The semi-axis of this ellipsoid are given by this lengths, which are the inverses of symmetric residual capacities. And now on this ellipsoid, we basically minimize the linear function given by the grid, right? So you move, and that gives you your next point F plus delta, right? This is the classic step in interior point methods. Here is our new ingredient. We propose an L1 interior point method. Look, we take a strictly worse upper bound. Instead of L2 norm squared, you replace that term with an L1 norm squared, right? It's strictly worse. Okay, but what do we gain? So now the inner problem sort of like, instead of taking this ellipsoid, we are embedding an L1 ball strictly inside the ellipsoid, and your goal is to find something like the vertex of this L1 ball where you minimize the gradient limit. Right, that's our L1 IPM. So the problem that you get formally is the following: that over circulations, find a circulation delta that minimizes the ratio of the gradient term divided by the L1 length of the circulation. Right. So previously in the electrical flow problem, we wanted to minimize the ratio of the gradient to the L2 length of the problem. Now that has changed to gradient over L1. Right. We call this the min ratio cycle. Okay. So let's spend the next 5 minutes sort of just interpreting this min ratio cycle and see that the problem is actually pretty easy to state. So let's work with this example graph here. The numbers in red are the lengths on the edges, right? So you have two sets of numbers. The numbers in reds are the lengths. Then you have gradients. These numbers in black are the gradients. But remember, gradients have to have a direction, right? I have to specify that the gradient on this edge is positive 4 if the flow is in this direction, and the gradient on this edge is -1 if the flow is in this direction, right? And we are looking to find circulation. So the simplest circulation is a cycle. Let's say you send 1 unit of flow along this cycle. What's the length of this flow? Well, that's easy. That's just going to be the sum of 1, 2, 1, and 2. That's 6, right? What's the gradient contribution? Just as a simple example. So along this edge, the flow is against the gradient. So you get -4. Along this edge, the flow is against the gradient. So you get +1. Again, against the gradient. So you get +3. This one is along the gradient, you get +1. Right? So that gives you +1. And if I was to reverse the direction of the flow, the length remains the same, but the gradient contribution flips side. Right? So this is the part I want to emphasize about this problem, that the edges and lengths are undirected. In the sense that by the edges undirected, you can send flow in either direction. There are no hard constraints on this problem. Right? The length contribution also doesn't depend which direction you flow in. But the gradient has a direction. So your gradient contribution depends on whether you're flowing along the gradient or against it. Right? So in that sense, it's a problem that's intermediate between directed and undirected. We've gotten rid of hard direction constraints on the edges, and that's a big advantage of using interior point methods. But the gradient sort of still encodes mild information about directionality. Right? Questions about the min ratio cycle problem? Okay, awesome. Here's one more very interesting observation. Why is this problem interesting and simple? Because you're working with the L1 norm now rather than L2, you can assume that the optimal solution is a simple cycle, right? Just by linearity. This is just not true of the L2 problem. The L2 problem, in fact, will basically have non-zero flow everywhere. But solutions to the mean ratio cycle problem can be more compactly represented as cycles. Great. So here's a theorem about the L1 IPM. Prove that there is an IPM for maximum flow such that one, you need an almost linear number of iterations, m to the 1 plus little o 1. At each iteration, you are asked to solve a sub-problem that's a min ratio cycle, right? So you get a gradient and you get lengths, and you want to solve the min ratio cycle problem. Importantly, you don't have to solve them exactly. If you solve them approximately, that's good enough, right? Even crude approximations are good enough. And right, if you get a kappa approximation, you'll pay some kappa square in the running time, and that's it. Right? So you can solve them approximately. And thirdly, these are not independent problems. Actually, the gradients and lengths are changing very, very slowly. On average, in a typical iteration, you'll only get constant number of coordinates changing in the gradients and the lengths. Right? So you can actually hope to do something, given that these problems are so closely related and don't change significantly. Okay. Finally, I have to guarantee that these problems are all have a good solution. We actually guarantee something much stronger. They actually have one single hidden direction, which is a good solution, which is the direction from your current solution to the hidden optimum. Right. So at any iteration, if I look at the direction f star minus f, so I don't know f star, right? That's the hidden optimum. But if you evaluate the quality of that direction, that gives you a good solution to the mean ratio cycle. Right? So not only are they related in the sense that the gradients and lengths are not changing, in fact, they all share a hidden solution right? Basically a common hidden solution, the direction to the optimum. Right? So that's all I was hoping to say about the L1 IPM, but I can take questions. Yes. Yes, the main reason is that basically we'll take small step sizes. Once you're taking small step sizes, then the length and the gradient just cannot change too much. Good. Thank you. So good. So let me just repeat the point. Why did I say that the gradients and length actually they change everywhere? But the main point is, unless the change is significant, you don't have to do anything. So let's think of the length, for example, right? Unless the length doubles, I know I'm within a factor 2 solution, and that's good. Right? So we will only change the gradients and lengths in the sub-problems. Like I'm sort of hiding the distinction between true gradients and the approximated gradients, right? But basically, unless they change significantly, we will not touch those coordinates. Right? And so in that sense, they are stable. You're right, exactly right. That the exact gradients and lengths will change, but overall, if the changes, if all the lengths change by a factor 1%, I don't care. I can just solve take the previous direction and yeah. Yes. That's right. That's right. Second question: why is M1 so good. So okay, good. So I could, like, if we had bored in 5 minutes, I could completely answer that question. So the way to view it is easy to find a point which has potential value something like m log m. That's your starting point. And it's also easy to observe that if your potential value is, say, less than minus 100 m log m, minus 100, then the log value terms are actually they don't matter. They are positive actually, right? And then since the log, no, sorry, what am I saying? The log barrier term cannot contribute too much negative. Sorry, that's how I should say, because it's, let's say all capacities are 1, right? So you have minus log Fe minus log 1 minus Fe. So it has a strict minimum, which is some small constant. So that can only contribute something like minus m. So this means that the first objective term is contributing a large negative value. So you must be close to the objective, right? So the goal is to go from something like m log m to minus m log m in terms of the potential value. And at every step, I'm guaranteed that you can do something like constant progress. So you get m log m iteration, right? That's sort of why m log m iteration is suffice. Right? Does that answer your question? Any other questions about the IPM? Okay. Okay, awesome. So by the way, how long do we typically go? Okay, awesome. Good. Not one, right? Then I would have. Okay, super. So this is our first key ingredient, L1 IPM. So now the question is, can you solve this sequence of min ratio cycle problems efficiently as they slowly change from one to another? So that's our second key ingredient. It's the bulk of the paper. Something like 70 pages to solve this. I want to give you some of the key ideas that sort of go into it, and at least give you an appreciation for why this problem is significantly easier, right? Like, why don't we just go to the electoral flow and why it's significantly easier? So let me first show you why it's significantly easier by just solving one instance of the problem. Okay, so I give you one instance of min ratio cycle. So you're given gradients, length. You want to find an approximate solution. So you want to find a circulation that approximately minimizes the ratio of the gradient to the length. Okay, I'm going to give you an algorithm, and then we'll show that it's a nice algorithm. So the algorithm is based on trees. And it's the following two steps. We'll sample a random low stretch spanning tree. If you haven't seen this, if you don't know what they are, don't worry. I will define whatever we need about them. But it's worth knowing that they've been well studied, and we know how to sample such a low stretch spanning tree in almost linear time. Okay. So you sample such a low stretch spanning tree, and from this low stretch spanning tree, test the quality of every fundamental cycle and return the best of them. Right. So they're only, so what is a fundamental cycle? A fundamental cycle in the tree is take an off tree edge and complete that edge with the path in the tree. Right. That gives you a cycle. So off tree edge and the tree path. There are only roughly m such fundamental cycles, but you can check all of them, the quality of all of them, by using some dynamic programming quite efficiently. Right. Linear time, you can check their quality, and you return the best fundamental cycle, again in almost linear time. So the algorithm is efficient. That's pretty clear for one instance. For a single instance, you can run this in almost linear time. But why does this give you good quality? So let's talk of the quality, and I'll do a proof by example, a proof by picture, basically. So let's say this is a graph, right? I'm going to prove that one of the fundamental cycles is going to be a polylog approx with constant probability. So we said first sample a low stretch spanning tree. Let's say these blue edges form a tree. So now I need to tell you what is the guarantee of a low stretch spanning tree, right? So the distribution of a low stretch trees gives me the following guarantee, that if I look at any fixed edge, right? So let's say this solid black edge, look at any fixed edge, look at its fundamental cycle in the tree and its length, right? So the length of the fundamental cycle, that length in expectation over your distribution over the trees, right? So we are sampling from a distribution of the trees. You fix an edge, you sample a random spanning tree. In expectation, the length of the fundamental cycle is not much larger than the length of the cycle, right? You lose a log factor here, basically. That's it. Okay, so in expectation, this length is not large. So what does this imply? This means that suppose I have my hidden solution to the mean ratio cycle problem, this cycle in green. I don't know this, but now I can add up this guarantee across this cycle and say that in expectation, the sum of the lengths of the fundamental cycles is not much larger than the length of the optimal solution, right? Just by adding up over linearity, linearity of expectations. So by Markov, with probability half, I will sample a tree such that the sum of these lengths is not too large. So that says good. So the lengths are approximately preserved. What about the gradients? The gradients actually turn out to be in some sense simpler. The observation is that if I sum up the sorry about that. Good. So if I sum up the gradients for each of these fundamental cycles, the gradient contributions for each of these fundamental cycles, look at this. So in this cycle, I get this contribution. In the other cycle, I get this contribution. All the tree edges actually perfectly cancel, right? Every tree edge gets traversed once along one direction, once in the opposite direction. So you cancel them out perfectly. So you're exactly left with the gradient contribution of the original cycle, right? So sum of the gradients is preserved exactly. The sum of the length is preserved up to a log factor. So by an averaging argument, the best of these cycles must actually be a polylog approximation, right? Is this argument clear to all of us? Can answer questions of that. Super. So this actually demonstrates why the L1 is very nice. Like already we've seen two advantages. One, you can approximate these problems very well by trees, right? And these gradient terms, they sort of cancel in very nice ways when you look at these cycle contributions, right? So it makes her job much easier. Okay, so this gives you a claim for constant probability. If you sample log n of these trees, you'll get high probability, right? Like at least one cycle does well, right? So that's an algorithm for solving min ratio cycle for a single instance. Of course, we have to do it for many instances, and I will try to tell you more about that. But before that, let me try to state the theorem that we prove for the min ratio cycle problem. So we say the following. So we build a randomized data structure that will maintain a small collection of such low stretch trees, right? One will not be enough. We'll maintain a small collection of these. These trees will sort of keep changing as you change the problem. So it's a dynamic data structure. It supports several operations in basically constant time per operation, amortized. So you can change gradients and lengths, right? That's the first thing we wanted. That if I change, I should be able to change the gradients and the lengths. Two, I should be able to return an approximate min ratio cycle, right? Right. You've got first problem. The second problem, you need to find an approximate solution. You can do that in almost constant time. I want to iterate that these cycles need not be small, right? These cycles can actually be very large, involving lots. So what does it mean to return such a cycle in almost constant time? Means that they are basically some fundamental tree cycles and union of them, and which they have a compact representation, right? On a fundamental tree cycle has a very short representation. I just tell you the pairs of vertices, or rather the off tree edge, and that gives you the cycle. And these cycles will be described by a collection of a small number of fundamental tree cycles. And third, of course, you want to support that, hey, please route some flow along the cycle in order to move to the next step, right? And we are going to support these operations in almost constant amortized time with high probability, actually against a somewhat adaptive adversary. No, actually, the cycles can all be long.
Wasn't the previous statement
The L1 IPM view?
the number of
Update of gradients and lengths is small, but the optimal cycle could always be huge. No. So good. So in terms of sending flow, right? So right. So let me just go back to the. So no, we have to update the whole cycle. So the way to think about it is, let's say the tree is a path, right? And I say that the fundamental cycle is actually this of is a good mean ratio cycle solution is an off tree edge from the first vertex to the last vertex and the entire path. But I can basically maintain an efficient data structure over the entire path and route it along it in polylog time, right? So we do update it, but we have to update it very efficiently by using basically dynamic tree data structures, right? So then basically these tree data structures allow us to have efficient representations and efficient data structures for updating and querying values. More questions? Yes.
So you're maintaining these trees,
right?
like samples from the
Kind of, yes.
But, when you update them, they're not,
Excellent. So excellent, right? So that is really a big issue. The first step, they will be independent. You find a solution, but now your solution is conditioned on good randomness, and you no longer have independence. So that really is a big issue. Here I'm mostly hiding it under the rug, but I'm happy to answer questions about it. So I will show you ideas for a data structure that works for an oblivious adversary, right? But of course, our adversary is not oblivious, because the updates we get are dependent on the solution we return. But it's also not an arbitrarily malicious adversary. It is coming from this IPM, and the IPM guarantees that actually there is always one fixed hidden direction that is a good solution. This hidden direction will help us make changes to our data structure by basically saying that, oh, there are only a few edges that might have gotten ruined, and I will take care of them. So it's crucial for us. We cannot solve the mean ratio cycle problem, or at least we don't know how to solve the mean ratio cycle problem against an adaptive adversary, but we can solve it against the IPM algorithm, which is adaptive but not malicious in some sense, and it's constrained by the fact that there is a good. You have to maintain that the direction to optimal is a good solution, right? Did that point make sense? Right. So I'm not even writing it here, but it's something I'm hiding under the rug, and it is an important issue. Okay. So right. So this is sort of like, I mean, I'm really writing a cartoon version. There's a lot going on, and I have to tell you more about it in the next 15 minutes. Right. So we want to prove such a theorem. So but once you have such a theorem, here's roughly what our algorithm looks like, right? So just to complete the picture, so the algorithm has a data structure that maintains a few trees, right? It loops for almost linear number of iterations, m to 1 with the 1 plus little of 1, where we at every iteration you update, send gradient and length updates to your data structure. The data structure uses these lengths to update your trees. From these trees, now it returns a circulation that's an approximate solution. You send a small amount of flow along the circulation. Now we go back and repeat. Right? That's what the entire algorithm looks like from a bird's eye view. Okay, so I want to tell you now over the next 10 to 15 minutes about like some ideas that go into this data set. Yes. On average, yes. So right. So there is the step that I'm hiding here is that the IPM will give you some exact gradients and lengths, but let's focus on the lengths. That's easier to answer. But some of them will have only changed by 1%. Some of them could have changed by a factor of 100. I only look at the edges that changed by where the lengths changed by a factor of 2. And I send those updates to the data set. And I'm saying that on average, only a constant number of or polylog number of coordinates will change lengths by 2. Right. So the gradient approximation condition, the gradients can also be discretized, but that's a little more tricky. They don't. It's not multiplicative; it's sort of additive, but scaled by your lengths. Right. So with so only the ones that change significantly we will report to the data structure. Okay, great. So let me try to give you a few pointers as to now what happens when you start trying to solve many of these iterations. Okay, so let's ask ourselves a question. So let's say at the first iteration, I'm willing to pay the almost linear time. You sample a random tree and it was good, right? So and now you get to the second iteration. So let's ask what happens when you go from the first to the second iteration. So from the first iteration, I have a good tree T, right? What does it mean? I have a good tree. That means that sort of says that that these edge routings, right? What do I like? I'm using this word routing, but it's the same that I take an off tree edge and sort of connect it back in the tree. These edge routings are not too long for some set of hidden the hidden edges that we care about, right? So these edge routings are not too long. So I have one such good tree, but when I go from iteration 1 to 2, suppose some of the tree edges now go from length 1 to length 100, right? So if the tree edges get too long, it's not good to use them in the tree anymore, right? Because that will ruin the guarantee that these fundamental cycles were not too long. Okay, so all of these dashed blue edges are now edges with much longer length. I don't want to use them in the low stress tree. All right, but of course I cannot afford to recompute the entire tree at every iteration. Can we do something cheaper in order to fix this tree? Right? That's the question. So some of the tree edges have been ruined. They are much longer than they were. I don't want to spend linear amount of time. Can I do something cheaper in order to fix this low stress tree? And the answer is yes, you can do something cheaper. And the key observation is that if I look at the part of the routing or part of the fundamental cycle that does not use these blue dashed edges, that's still good, right? Because it's only using edges that were in the original tree and are still basically the same length. And they were good by our assumption from the first iteration. So these partial routings are still good. I just want to fix and convert these partial routings into a complete routing. So to do that, I'm basically going to observe that I can sort of reduce it to a much smaller problem. How? So I look at the connected components from the edges in the original tree that are still good length, right? That didn't change significantly. These are the parts that have good routing still, right? I just shrink these connected components down to single vertices, right? So this component becomes a single vertex here, and you get this green edge becomes this loop, and the other edges sort of go across, right? So I get a much smaller graph. And my main claim is that if I find a low stretch tree, like we call this graph the core graph, that if I find a low stretch tree on this core graph, I can use it to patch the forest at the top level and get a lowish stretch tree. Your stretches will multiply, but log square is still fine. Right? Does this idea make sense? Right? So you couldn't use some of those edges, throw them out of the tree, you get forests, collapse those forests into a much smaller graph we call the core graph, find a low stress tree on the core graph, and then use it and join it with the forest to get a tree that is still good. So now you're solving a much smaller problem on the core graph, right? This is much more efficient than resampling the entire. Okay, so that's one piece. And the kind of guarantee you need is sort of a very simple lemma that if the tree was good, that means the forest was preserving my hidden min ratio cycle, then the core graph also preserves the min ratio cycle if you define the lengths appropriately, right? Like my lengths have to sort of go up with the stretchings because of the partial routings, but if you define the lengths appropriately, the core graph also has a good min ratio cycle. So I can now recurse here and then and lift it up. Okay, so that's one key idea. Core graph, this gives you vertex reduction, right? You can go from n vertices down to, let's say, n to the 0.1 vertices and solve smaller problems. I need to identify that we need to maintain this core graph as you are making changes at the top level, right? At the top level, I'm changing edges, right? Edge lengths are changing. Every iteration I get a core graph. I don't want to rebuild it every time either, right? You want to maintain this core graph as it undergoes changes. What kind of changes does the core graph undergo? Well, some are easy. So edge deletions, edge deletions from the top one, edge insertions from the top one become edge insertions here. But look at edge deletions, look at a tree, say, let's say, so this is after iteration 2, right? At iteration 2, I constructed this core graph. At iteration 3, say this black edge gets elongated again. So I can no longer use it. What does that do to the core graph? That means this component splits into two pieces, right? If this black edge cannot be used, this component splits into two. So I get a vertex split in the core graph, right? So I'm going to maintain this core graph under edge deletions and vertex splits, right? So that's one piece of the dynamic algorithm puzzle, or at least the key idea behind it. The second piece that I will try to sort of give you an idea of very briefly is yeah, let me see, is that just doing this core graph is actually not enough. Let me tell you why. So the answer is almost here. So when a core graph undergoes vertices, remember we've reduced vertices. Okay, so from n vertices, I've gone down to n to the 0.1 vertices, really few, but the edges have not reduced. Right? I might still have m edges, and if I have a high degree node and I split it, that's just too expensive, right? If it was basically a star graph with m edges and I split it into m by 2 each, it's a lot of work that I can't afford to pay at every iteration. So you need a way to not track all the edges and do edge reduction, and that edge reduction comes via by building an explicit spanner of the graph, a spanner of the core graph. Okay, what is a spanner? So a spanner is a sparse subgraph, right? So here in this core graph, instead of all the green edges, I will take these blue edges, which are a subgraph, and I guarantee that every green edge has a blue path that's not much longer, right? So this is a spanner that's preserving lengths up to polylog factor. Excuse me. Right, so we will maintain these spanners that will allow us to reduce the edges by a significant factor. Now down to roughly the size of your vertices n to the 0.1. Okay, and the challenge is to maintain the spanner not only just as a subset of edges, but actually we want explicit paths for every edge that's not in the tree. Right, because how, like, I want to send an edge along this flow along this green path. How do I route it in the spanner? I sort of need that explicit path to maintain the quality. Okay, and the main lemma that we show is that if the core graph, so the green union blue, if the core graph had a good mean ratio cycle, then one of two things happens. We show a dichotomy, right? So last time we said if the original graph has a good mean ratio cycle, the core graph has a mean ratio cycle. Here we'll show a dichotomy. Either your spanner has a good mean ratio cycle, that's good. Now you can recurse on the spanner, or one of these fundamental spanner cycles is good. What is a fundamental spanner cycle? Take a green edge, look at its blue path connecting the green edge, and this cycle is good. So one of these fundamental cycles is good, or the spanner has a good solution. So you check all the fundamental cycles or recurse on the spanner. Right? Okay. All right. I will wrap up with this. So we basically give a dynamic maintenance of the spanner, undergoing edge updates and vertex splits, and with a lot of nice guarantees. I mean, so dynamic spanners have been studied, but we really needed some further stronger guarantees that were sort of not known in the literature. So we had to sort of prove it from scratch. One is for every edge we maintain explicit embeddings. Two, these embeddings are not only are these embeddings short, they also give small congestion, in the sense that each of the edges in the spanner does not have many embedding paths going through it more than the average, right? So they have small congestion, and you can basically maintain it the small amount of amortized updates per iteration. Okay, so I should completely wrap it up. I will just now start to zoom out. So what does this tell you about the entire data structure? We have to layer our vertex reduction and edge reduction in a hierarchy. And here's how it looks like. So at the top level is your original graph. For this original graph, we were sampling log n low stretch spanning trees, right? Or these are rather forests because some of the edges got deleted. Each of these forests, once you contract the forest, you get smaller graphs, which we call core graphs. We maintain these core graphs, and on these core graphs, you maintain a sparse subgraph called a spanner. This becomes level 1. And now we recurse on this level 1. You pick log entries again, and you build a second core graph, and you build a spanner all the way down to level D. And we will maintain this entire data structure dynamically throughout the algorithm. Okay, very efficiently. Few observations, you sort of get this increasing fan out. You have log n to the I graphs at each level. The main guarantee is that, in fact, if you take any edge and you average over, so okay, so I should let me maybe also say one more thing that will make, if you walk down one of these paths in the data structure, you actually identify a single low stretch spanning tree. How is that? Well, we had forests at one level, then you contracted that graph, then you picked another forest, then you contracted that graph, you picked another forest. You patch all of these forests, you get a single tree. Right? So every path in the data structure corresponds to one tree. So we have something like log n to the D trees that we are maintaining. If you average over these log n to the D trees for any fixed edge, your stretch is m to the little o 1, right? So we are maintaining low stretch for any fixed edge, right? And this will allow us to find good fundamental cycles. And yeah, we can maintain this efficiently. Okay, so let me skip this. I also skipped one more key idea, which you had a very nice question about, is that what I showed you will work against an oblivious adversary, right? We sampled independent and we sort of never fix the randomness. We have to work with adaptivity, but the key thing is that that we actually we know there is a good hidden certificate. We'll exploit that to work against an IPM adversary. And let me end with that. And thanks to the co-authors, and thank you for listening.